Imagine you have a list of tasks to complete by the end of the day. Let's say you need to buy some groceries, make dinner, clean up after dinner, and do your laundry. You want to complete all these tasks in the least amount of time. The sooner you finish, the sooner you can relax and watch some YouTube videos. Notice that some of these tasks depend on others. For example, you can't clean the kitchen until you cook dinner, and you can't cook dinner until you buy the groceries, and so on. In what order would you do these tasks? Well, looking at the graph, one naive approach would be to pick a task with no predecessors to work on. Once done, remove the task and we repeat, working on tasks and then removing them until we are all done. For this naive approach, let's take a look at what the pseudocode may look like. If given a set of tasks, at each step in time, we are searching for a task with no predecessors. As for the time complexity of this approach, skipping over some details, this would be big O of n squared, where n is the number of tasks. But now, let's imagine that we have a lot of tasks, too many for just one person to handle. So we call up someone else, maybe a friend or sibling. Now that there are two people working on tasks, how should you divide up tasks between you and your partner? Before we can look at the solution, let's formalize this problem so that it's easier to generalize. We can refer to tasks as T subscript 1, T subscript 2, and so on. We'll call the two people working on tasks P1 and P2. In computer science terms, we can think of them as processors. We'll also keep track of the tasks P1 and P2 are working on. Currently, it can be seen as empty. We'll also use the Greek letter mu to represent the current time step. For now, we'll assume that each task takes exactly one step of time to complete. Later on, we'll explore what happens when each task takes a different amount of time. Lastly, the schedule produced by P1 and P2 we shall call L. It will keep track of the order in which tasks are done. Now let's try processing these tasks using the same method as before. At each time step, we pick any task that has no remaining immediate predecessors. Once a task is complete, we update the graph and continue choosing the next available task until everything is done. All the tasks are done, and we can see that it took 5 units of time to complete all 8 tasks. But can we do better? If we go back, we can see that there are 2 time steps where P2 wasn't doing any work. So maybe there's a more efficient way to schedule tasks. This question was studied in the early 1970s, and an algorithm was found by Edward Coffman and Ronald Graham in their 1971 paper, Optimal Scheduling for Two Processor Systems. I will be referring to their method as the Coffman-Graham algorithm. Here is the full definition of the Coffman-Graham algorithm, as it appears in the original paper. The full definition is a lot to take in, so we won't be using this formal definition for now. Instead, we'll step through an example to build an intuitive understanding of how the algorithm works. Let's go back to the same graph we had before. Why was our schedule not optimal? Just to prove to you that the previous schedule was not optimal, I will quickly show a better schedule, in fact, the most optimal one. Notice that at each time step, both processors are working on a task. This means we reached the most optimal schedule since there was never a time where we could have done an additional task. But anyways, how do we find the optimal schedule in the general case? Well, notice that at each time step, we get to pick tasks to work on. A natural follow-up question would be, during each time step, how do we figure out which tasks to pick for the optimal schedule? Let the optimal schedule be denoted as L star. For now, it's still in progress, so it's empty. The Coffman-Graham algorithm states that we fill in L star in reverse order. Basically, this means we figure out which task to do last, and then we work backwards until we finally figure out which task to do first. To illustrate this, I will fill in L star with blanks that will eventually be replaced by some task. There are 8 tasks, so I will put 8 blanks in L star. But why should we do this? Well, in a sense, we are looking for tasks that can be done later, as other tasks could be higher priority. For example, in this graph, it's difficult to say if we should start with tasks 1 and 5, 1 and 8, or 8 and 5. But it is easy to see that tasks 2, 4, and 7 can be done as later as possible, as they all have no successors. In other words, tasks 2, 4, and 7 can be done as late as possible because they don't have any other tasks waiting for them to be done. So let's put 2, 4, and 7 in the last blanks of L star. It should be noted that their order doesn't really matter. I'm simply putting them in order of their subscript for visual purposes. Now that L star is starting to get populated, I'm going to write down the position of each task in L star next to each task. We will see how this is useful later. Now at this point, we want to figure out which task to do fourth last. So how should we choose the task? Notice that for any task we choose, that task will have at least one successor. What the Coffman-Graham algorithm states is that we consider all tasks with successors defined in L star. So in this example, task 3 has its successors, task 4 and task 7 defined in L star. So we will consider it a potential option. This is also true for task 6. Notice that this is not true for task 1, since task 3, its successor, is not in L star. This was a lot to unpack, but now we narrow down which tasks to put in L star next. Remember, from this list, we want to figure out which task to do as later on as possible. At this point, we have an array of 2 candidate tasks. We reach the heart of the Coffman-Graham algorithm. For each task in our list of candidates, do the following. Find all of its successors in L star and populate some array with the indices of its successors in L star. Then we sort the indices in descending order. And that's it. We do this for every candidate task, and we are left with a decreasing array for each candidate task. In this example, we only have 2, but in a larger task graph, we could have many candidate task arrays. All we have to do at this point is find the array with the lexicographically smallest array. Once we found that task, we put it in L star at the last blank index. And that's it. We repeat this process until L star is completely filled in. To recap the Coffman-Graham algorithm, given a task graph, first we make an array L star with size equal to the number of tasks. Then we consider all tasks with no successors and put them in some order at the back of L star. Then, until L star is filled in, do the following. Consider all tasks whose successors have indices defined in L star and make it a candidate. But don't make a task a candidate if it's already defined in L star. For each candidate task, make an array with each element being its successor's indices in L star, sorted in decreasing order. Then, pick a candidate task with the lexicographically smallest array. At this point, L star is completely filled in and is the optimal schedule for the task graph. That's the Coffman-Graham algorithm.